All right, so we're CosmIC. We're the radiation-hardened, hardware-accelerated FFTs and matrix multiplication. I'm Varun, and my other three teammates are Lohith, Dave, and Sid. So the project context, in terms of motivation, we're looking at a space economy growth. So as the years have gone by, there's a reduced cost to launch, and therefore there is increased spacecraft deployment. As such, there is a demand for inexpensive radiation-hardened electronics, and that's where radiation hardening by design comes in. So the big context behind why radiation hardening is important is because of single event upsets and other types of single event issues. This can cause, in our case, what we're targeting is causing these unaccounted for bit flips. So things, different parts of different systems can have bit flips where the changes, for example, it could change a computation output or it could change a operation code or something of that sort. Traditionally, TMR or triple modular redundancy is used. And of course, with TMR comes with that 3x area overhead, so it's really inefficient for a larger scale computation and can cause cause a lot of more power draw as well. So CosmIC's innovation is combining this interval arithmetic and forward error analysis for radiation hardening. And then we are really aiming for a lower area than TMR while maintaining that fault tolerance, and we have shown that it is possible. The key question here is that can reduced precision computations tolerate bit flips while enabling area efficient hardening? So if you look at interval arithmetic, we have what we call a triplex. So you have a low value, a center value, and a high value. And so you have a higher precision center and lower precision guards. So these guards are exactly one unit of floating point distance apart, and they form the guards around the center value. And then you have addition, subtraction, and multiplication. These are the different types of operations that you can do with interval arithmetic. And you can see here that the multiplication operation is a little bit complex, and it's really nice with the operations that we're doing, especially with the FFTs, that we're using constant to triplex multiplication, which is different from this. In terms of our innovation, we're really targeting this application or algorithm-based fault tolerance. So we're really utilizing the inherent properties of the application in question, and we're really striving to make a more efficient redundancy and error detection system. And so our application here is known error and FEA, or forward error analysis. We can really accept a lower precision for both FFTs and deep neural networks in certain applications, and those are the applications we're targeting. Like, for example, there are some aspects of audio analysis that you can use FFTs for that don't necessarily need to be very precise. And so you track the expected growth of the interval throughout the entire operation, and you compare it with the actual growth at the end. That's the defining principle of this application.
Now let's look at the tape out specifications. We're working on the 28 nanometer process. Our die area is 1 millimeter squared, 1 by 1, and we have around 200,000 gates. The max frequency that we intend to operate at is 500 megahertz, and our power consumption is 190 milliwatts as measured by Innovis. The total amount of I/O pins is 44, 23 I/O pins and 21 power ground pins. And one of the changes that we made that we had mentioned in the last presentation, but we'll say again, is we initially wanted to use SRAM, but given our limited memory that we would have, we actually find the area overhead to be quite limited when we switch to registers. So for input, we have 8 16 by 32 registers for FFT and MAC, and for the output, we have 8 16 by 32 registers for FFT and MAC. This is a change from last time when we had 16 instead of 8. This is the sort of top level flow here. So we have the input registers and MMIO at the beginning here. And generally the user will have two choices as to how to generate their inputs. They can create their own inputs by storing them in memory first and then loading them in, or they can randomly generate them with our on-chip LFSR unit. Whichever mode the user wants to choose, these inputs will go into a triplex conversion unit, which will generate the guards for each of these inputs, and then they will go through either the FFT module or the MAC module. The user can choose that as well. and then those go through their own interval checker, which checks if a bit has been flipped, and then they go into output memory.
Moving on to our I/O, you can see that we have 8 clock pins, which are mandatory, and most of them correspond with essentially allowing us to configure our clock in terms of frequency, as well as choose between whether we're using our onboard fast clock or an external manual clock, which is much slower. And so then we have 3 control pins, which basically allow us to make sure that our chip is actually getting I/O power properly and that our chip is alive. So then moving on to our SPI pins, this is the main form of configurability in our chip, which essentially allows software to set the MMIO registers and control the operation of the chip. So to continue, we also have a synchronous reset, and then we have a scan chain, which is basically for testability and basically allows us to verify the operation of our chip. And then we have the ECU scan chain, which is allowing us to insert bit flips into different portions of the chip and allows us to determine whether our chip is robust to bit flips. Then moving on to our power and ground domains, we have the I/O domain, we have the clock gen domain, and then we have 2 different domains. One of them goes for the PDA, which is essentially the MAC and FFT, and then we have the PDB, which is going for all of the peripheral logic, which stores our data in the input and output memories, as well as the LFSR.
So the inputs can come from one of 2 places. The user can send them via SPI to the input memory, and those can be used as inputs, or they can be sent or randomly generated by the LFSR. And these inputs can be sent to one of 2 modules, the FFT or the MAC unit, and the user can indicate which one. And in terms of the flow, again, the data is sent through one of these 2 modules, and then each of them has a validity check. And if the output is actually invalid, then we actually retry the unit until the output is no longer invalid. And in either case, the output results are sent in memory and are read out using SPI. So here's how the inputs are generated. So again, the inputs can come from either the memory or the LFSR, which is what this MUX is for both the FFT and the MAC. The LFSR consists of 16 small LFSRs. They each have a seed that the user can customize. And whichever one, either LFSR or memory, there are guard generators that generate the guards for each individual input and sends these triplexes as input to either the FFT or the MAC unit.
Okay, so this is the MAC, and you can see that we have a 4x1 systolic array of fuse multiply add units. So the fuse multiply add unit is purely combinational, and it's composed of a Booth multiplier along with a Wallace Tree adder, as well as some other things. And so we also have the checker, which is basically going to generate the is valid signal, and it determines whether the center value is inbounds. And so the reason why we have the MAC unit is basically to demonstrate that this type of radiation hardening is not purely restricted to an FFT. It's generalizable to float operations.
So we also have a radiation hardened FFT accelerator. So the FFT design is a radix 8 design, so it's doing an FFT 8. It is a high throughput architecture made to be able to run to about 1 gigahertz, and it's really optimized for satellite signal processing. So things like spectroscopy or communication. And then we have the checker at the very end that really bounds the computational errors by tracking the ranges of the exponent values, and then And then you also detect out-of-bound results due to those bit flips and retries. Now, a key part of this DFT module is that the inputs are bounded from 0 to 1. And so this allows us to make sure we have a max exponent value. And so we can actually normalize the high and low values to be able to accurately calculate the distance. And so you can see here in the checker, we have 3 different characterizations we're looking for. So 3 different conditions as well we're looking for. So we want to ensure that the low is less than the center, which is less than the high value. We want to ensure that the low exponent, the high exponent, and the center exponent are less than the maximum exponent. So in this case, with an FFT 8, the value should only go up to 8 maximum. And then we also want to check if the high minus low value of the actual triplex is less than that critical path error growth. And you can see as well that because we have 16 triplex outputs, we do a 16-bit NOR reduction to essentially just see if a value is 1, it should be the entire is valid should go to 0. And then you get the 16x single precision outputs. In terms of our fault injection system, we want to be able to implement fault injection to mimic the single event upsets. So we have what is called the error control unit. So this is really a scan chain that's dedicated to the FFT module itself. We're going to be injecting errors using an off-chip scan chain in the FFT unit, and then generating that report in the FPGA with an error count of false positives and false negatives. So all of these are added, the scan chains are added during the synthesis process, and they have been added. And the ECU module was initially actually planned to be on the chip itself, but it actually ended up being for area's sake and for more robustness sake, we decided to go off chip on the FPGA. And then in terms of the rate of injection, the error rate in terms of like how many errors per how many cycles is coded into this off-chip FPGA implementation of the ECU. And then in terms of the method of injections, so after the X cycles, which is part of the rate of injection, the ECU scans out values and flips a random bit. And so the initial implementation of the ECU was to have a shift register to hold the entire contents of the FFT and then flip a single bit. But instead, we're using a counter, which is a lot more area efficient, and just flipping the bit as necessary. And then the operation then continues with the errors tracked. So in this mode, where we're using the ECU, ideally you'd be using the LFSR values that are kind of randomly generated, and you wouldn't actually stop the operations when you detect an error, so we could get a much more in-depth characterization of what the actual errors should look like.
So here is how we send data in and out of the chip. We use an MMIO-inspired protocol. Basically, we send in packets of 64 bits. The last 32 bits are the data associated with each instruction, and the first 32 bits consist of, first of all, a bunch of ones, which is our instruction header, then some bits corresponding to whether we want to read, write, or clear some specified register, a few zeros, and then an address, a 16-bit address of the register that we want to read, write, or clear to. So for example, there is a register designated for starting the FFT that we can write a 1 to start the FFT. The hardware clears it to 0, and the FFT starts. And then the FFT will write a 1 to the FFT end register, and then the user will have to read it to clear that. And this is 2 examples here. The MAC addresses have a similar thing here, and the user can always read these registers to get their value from them. There are also many different other registers like the LFSR seeds. The user can send this address as a bunch of A's here and then read and write those values. You can also set the number of computations that are done. They can also set whether they want to do the FFT or MAC. You can also set the test mode, whether we want to get the input values from memory or randomly generated from the LFSR, and the LFSR reset, so that we can, when we set the LFSR seeds, we reset the LFSR so that those seeds are actually used. And finally, we can also read and write from the two memories as well. We can, for both the input and the output memory, and those for the specified addresses there.
Okay, just to go over a couple of our final PNR outcomes, as you can look at the flow plan on the right, we have a total of 4 power domains where one domain is dedicated to the IO pads, one is dedicated to the accelerators, which is PDA, one is dedicated to the clock gen, and one final one for the actual logic, which is a PDB domain. The IO pads are supposed to run anywhere between 1.2 volts and 1.8 volts. And given our testing will be primarily done using an FPGA, the IO pads will be most likely run with 1.2 volts. The accelerators are synthesized to work with 0.9 volts, however, it should have a decent amount of tolerance. The clock gen has also been synthesized to work with 0.9 volts. However, this value is supposed to be variable given that a change in the voltage actually changes the on-chip clock frequency, which we need to set to 500 megahertz. For the logic, our logic is also synthesized to work with 0.9 volts. Again, should have a decent tolerance for about plus minus 0.1 volts. For our 4 clock domains, we have a core clock domain which has been synthesized to 500 megahertz, where all the logic should function with a 2 nanosecond period. Our scan clock, which is going to be coming from off chip, is set to be 10 megahertz. And similarly, we also have a SPI clock for our SPI communication, which is also going to be off chip and also synthesized to work with 10 megahertz. And finally, we also have a port for an external clock. However, this external clock will most likely be tied to ground, since it's supposed to be acting as a clock gate for when we want to turn on and off our core clock, which we just do by switching the clock mux from core clock or external clock, which would just be a ground. In totality, we have 44 pads, as we already talked about in our previous slide. We have 21 power ground pads and 23 IO pads. Talking about a couple of our final PNR outcomes, just looking at the Innovis final report, we saw that a total power with no activity is 190.75 milliwatts. And going through a voltage simulation of a realistic test load scenario, we saw the 19 milliwatts top activity was seen with pretty high current draw, but we have enough decap in our chip to combat that. There are no setup time violations, no hold time violations as is required, and any other metrics such as cap, tran, fan out, and length violations are within acceptable range. We also have 16 glitch violations, but again, just looking at the simulations, it does not seem like they'll be causing an issue in terms of actual chip activity. Our pre-metal fill density ended up being 66.577%, and with fillers and metal fillers, the final density comes out to be 98.514%. Just going over a couple of our test plans, in 18725, for most of our modules, we made a corresponding test bench, where for the FFT, we had a basic and a stress test bench. For Mac as well, we had a basic and stress test bench. We did some basic SPI communication tests as well, just to see if the protocol was functioning as expected. And then finally, just as a surety test, we had SPI to memory interaction tests, where we sent in a command to populate the memory, execute, etc., etc. And finally, an integration test bench where we did every single command in succession as required, where we'd set the memories, execute an operation, set the outputs, and then get the outputs back out from the chip. We also conceptualized a set of test vectors which would which ensured a coverage of a subset of possible single event upsets. We tested the ECU component as well, and in totality, we just wanted to make sure that if we do have a bit flip, can our chip actually find this error? And we had single bit flip tests and also multi bit flip tests, which were done through manual stuck at error analysis and etc. For 18726, we intend on having our basic tests like heartbeat and echo. We also plan on testing the full system run, where we do a single FFT Mac run all the way from input to output. We also want to do a high throughput FFT Mac run, where we set up a set of input vectors which it should theoretically run in succession one after another. We also want to test the built-in test capabilities, where we want to just see the scan in-out correctness, if the scan chain is working as intended, and also to use the scan chains to ensure that the as valid signals are being set at the correct point as we needed them to be. We also wanted to test the microcontroller interaction, which just to see if the SPI is compliant. However, it seems like given the fact that our ECU is going to be on an FPGA, the SPI interactions will also, instead of a microcontroller, be done on an FPGA as well. Just on-chip protocol procedure, just to see if it's looking at the correct codes and whatnot, and also to see if the triplex conversion registers are receiving the correct memory values. We also want to test the efficacy of the new architecture against the nominal case, just the correctness efficacy against TMR, error detection comparison against TMR, and also to see if just synthesize an old architecture in FPGA for a direct comparison, like apples to apples, bananas to bananas comparison. But thank you for listening to our presentation, and if you have any questions, please direct them to us and at our emails. But let's make CosmIC out of this world.